Hello, I'm Benjamin Cano, and this is the Nomadic Labs Research Seminar. Today we'll have a presentation by Thomas Gazagnaire about how to package Tezos as a MirageOS Unikernels. And this is a recording of Thomas, so we'll have a question and answer session with Craig Ferguson and Anil Madhavapedi from the MirageOS project. So enjoy the video. Thanks.
Hello everyone, thank you for attending this session. I'm Thomas Gazagnaire, the CEO and co-founder of Tarides, and today I will present you some work that we've been doing on MirageOS and Tezos. I would really like to stress out that I'm presenting this talk today, but the actual work is done by a rather large team of people working in Tarides, but in other companies too, and some of them are attending that presentation and will be able to answer to your question at the end. So first of all, let me start this session by a short explanation of what we do at Tarides. So Tarides is a software company created 3 years ago. We work on open source projects, and we try to build better systems by using a more scientific approach to software construction. I met my co-founders at the University of Cambridge about 10 years ago, and we worked since then together in various academic and industrial institutions and startups of various sizes, including Zen and Docker. Today we have around 35 engineers working on our projects, specialized in systems, in programming languages, and security. We are mainly based in Paris, but we also have employees working all over the world. So this talk today is split in 3 parts. First, I'll present you a bit of context about the general direction beyond our open source project at Tarides. Then I'll make a deep dive on what MirageOS Unikernels are. And last, I present the work in progress that we've been doing to package Tezos as a MirageOS Unikernel. So first of all, our expertise at Tarides is at the intersection between programming language research and system engineering. We think that the research done in the programming languages over the last few decades can help designing better systems. They can help to formally reason about them, they can help to better understand them, and more important to us, they can help to better secure the systems. On the other hand, we also believe that system engineering, with its focus on delivery complete systems, addressing pain points of general users, can also help making programming languages research more useful and more impactful. First of all, when we talk about systems, we have like various kind of systems in mind. Maybe one of the most dreamed system for system engineers is what we call ubiquitous systems. These systems are pervasive around us. They are invisible to users, but very helpful. For instance, they can transform home into smart home, which can obey to the sound of your voice. They can transform cities into smart cities, which can optimize energy consumptions at scale and reduce crime rates. They can as well transform buildings into smart buildings, where people of various companies can work inside and optimize physical resource utilizations and empowering people collaborations. Unfortunately, in the real world, these systems don't really exist, and what we see instead is broken or untrustable systems. So like smart homes record private conversations with user consents and send them to centralized data centers. Smart cities are hacked by criminals and will blackmail the city officials to get poor supply back. Smart offices are spied to optimize like the usage of resources, and the video of people going into the building, including going to the bathroom, are sent to without user consent again. And not very surprisingly, all of this make people more and more concerned about their privacy in these kind of computing systems where everything is getting more and more pervasive. So for Tarides, I think it's a concern, and we would like to build better systems for people to trust them a bit more. And so to do that, we have three main our approach of that is threefold. First, we think that the issue came from the cloud-centric architectures, and then using inadequate developer tools, and there's a general culture of layering complexity. So first of all, the business constraint causes most system designs to be done iteratively and to optimize time to market and time to find market fit and not security. And so this led to centralized systems based on central cloud services, which causes a lot of performance and security issues. From a user point of view, this system's architecture is very opaque. It is very unclear where the data is produced. Well, it's produced locally, but it's very where the data is consumed and sent and stored and proceeded. So instead of Tarides, we are developing what we call the offline-first architecture. So these are systems which do not need a global centralized state. That systems which can be synchronized only when needed, and where systems where the data is always processed locally by default. So we think that moving computation around is cheap and more secure, and data should not move around basically. And so the first project that we developed for this is Airmin, and that's was the initial use case, but it happens that offline first systems and blockchains share a lot of security and design constraints. And so today Tezos is using Airmin to store the context, so like the state of the ledger. Second, the inadequate developer tools. So it's not a surprise, won't be a surprise for anyone attending this seminar. But actually, we know what is the cause of the vast majority of software security issues. So if we look at the numbers, it's always interesting, but it's very consistent. So 70% of security issues for Microsoft Windows are due to memory safety issues. Same thing for Chromium. For Google, for Android, it's 90% of these vulnerabilities, and for like the known exploited 0 days, it's 80%. So the solution for Tarides, like for Tezos, I guess, is to use type-safe languages, which doesn't have this any kind of memory safety issue by design. So that's why we are at Tarides very involved in the OCaml ecosystem. We really like Rust as well, and we maintain most of the OCaml developer tools today. So, like for instance, Juno, PAM, Merlin, OCaml format, doc, with the help of the community. We are also super interested by making the language itself evolve, and so we are involved in the multi-core project, of course, and we are as well starting to do some more exploratory work across larger language features like modular implicits, or like adding specification language to OCaml, which is called Gospel, or trying to use OCaml as with interactive theorem proving. And the last issue, so the layering complexity. So this comes from like one of the fundamental theorem of software engineering, which is all problems in computer science can be solved by another level of indirection. And so as it started as a joke, but actually that's a bit like is really what people are doing in practice. And so this led to a culture where complexity could only increase. And so in practice, when a user deploys a new application, it also deploys a large, layered, complex systems which orchestrates access to physical resources. But so like for instance, when you run like a Unix process, it's run in Unix user space, pulling like shell libraries, and then that process need to access resources which are orchestrated by the Linux kernel, and then this itself needs to access resources which are orchestrated by the underlying hypervisor. And itself we are running on top of a CPU, whereas another operating system which as well orchestrates resource allocation. So all of these layers come with their own communities, their own tools, their own workflows, and of course their own security weaknesses. And it makes it impracticable. In practice, it makes it impossible for a software engineer to, when she writes an application, to understand all the code which is being pulled in and what the application exactly is doing at runtime. So I think a bit more concern for us is like we think as well that this kind of layered organization makes it impossible to apply any kind of formal verification process in practice, because like all the layers have different all the interfaces between the layers are all different, so it could be function call, but as well RPC, syscall, hypercalls, and all layers are using different languages, which makes like cross-language verification very difficult. Also, all the layers are very large and still growing, and so the amount of code which is involved is largely exceed what modern verification tools can handle. Last point, which is like what that seminar is about about reducing complexity. So instead of layering complexity, what we do is we build a new operating system, which is called MirageOS. So MirageOS is a set of libraries and a compiler, which helps create minimal, secure, and resource-efficient OCaml applications. So if an OCaml application only uses MirageOS libraries, and if the application is precisely described at compile time, so including configuration values, deployment parameters, and so on, so the MirageOS compiler can generate a Unikernel, and Unikernel is a single image, very specialized binary, which is fully independent of any underlying operating systems, and which contains only what is needed at runtime. And so, unlike traditional approaches, where the runtime context is highly dynamic, with like shared libraries, dynamic allocation of resources, dynamic scheduling, kernel modules, etc., Unikernels allow users to have a very precise control of the runtime context of their applications. And that's a very strong guarantee that it's very hard to achieve with other technologies. In practice, MirageOS is a large project. There's a lot of experimental libraries, but there's as well like very solid and production-ready libraries there. So it's used in Tezos, obviously, but as well it's used in Docker for Mac to handle all the traffic of the container running on the host. And it's used today by more than 3 million users every day. So to summarize, our approach to build functional systems is based on 3 principles. So we use offline first architectures, we use powerful developer tools, and we reduce the complexity of deployed applications. So these principles are all complementary. For instance, computation units have to be packaged as lightweight images to be moved around and closer to the data. Securely and in a cheap way, and so they need Unikernels. And then it's only safe to remove runtime check big Unikernels only because we are using a high-level language. And of course, as everything that we build, so the systems that we build are written in OCaml, improving the language itself makes our tools more efficient and more secure, and help us building better systems. So now let's dive into MirageOS. A bit of history first. So MirageOS started as a research project during Anil's Madhavapedi's PhD, where he was trying to build a functional internet, like re-implementing a lot of RFCs into OCaml and making sure that we have like a systematic way to re-implement these protocols. Later on, I joined Anil and Dave Scott in Zen Source to work on the Zen hypervisor, and we managed to boot the OCaml runtime on top of Zen. It was a first experiment that showed us that it was possible to do this kind of systems. But the project really started when we joined the Linux Foundation in 2013, and at the same time I was developing the OPAM package manager. And so the focus was really to integrate Mirage with the larger OCaml ecosystem and having a feedback loop between the 2 projects, as was the community. In 2015, we funded Unikernel Systems to develop the Unikernel concept a bit further, and it was acquired a few months later by Docker. And since then, we got a contribution for a lot of various organizations, including IBM with Solar5, which I will explain a bit later what it is. And 3 years ago, two companies were created to support the commercial growth of the MirageOS project. So Tarides, a company in France, and Robur in Germany, with the people who created the TLS implementation. Okay, so first of all, let's set up our assumptions and expectations. So Mirage cannot be used everywhere. So it's only designed for server deployments, so no desktop, and it's used and efficient only when you want to deploy only a single application with a single user on a known platform with a non-configuration options and with access to all the source code. So that seems very restrictive, but in practice, it's actually how most of cloud applications are deployed, and it's also in practice how most of the embedded software are deployed. So that's not so restrictive actually, but it sounds like. So now that you are in that kind of situation, what is MirageOS? So there's three components in Mirage. There's a set of libraries, there's a compiler to chain, and a runtime. First of all, the libraries. So MirageOS is a collection of large collection of libraries. There are more than 100 of them, which ranges from managing low-level network devices to network implementation, to storage drivers, and crypto libraries. Few highlights here. We have a complete re-implementation of the grid protocol, both the on-disk and the on-wire format. And we are implementing the TLS 1.3 specification with crypto primitive extracted from the Fiat project, which is we're using coq extraction. There's so for every so we are implementing a lot of internet RFCs, and for every RFC that we implement, we try to follow security best practice and recommendations. We try to build independent library that can be reused in various contexts. We use AFL fuzzing to make sure that we test it extensively. And when possible, we try to add some kind of formal verification against the semantics when it's possible. But remember that it's the internet, and so for most of, usually the specification is actually what the servers on the internet are accepting or not, and so it's not always possible. So we to avoid that, we compare our implementations against existing implementation and do some differential analysis. So when we talk about libraries, so this is all very generic libraries, but then we have some libraries need to access physical resources like the networking or storage resources, and then there's a few rules to follow. So when you write, for instance, a device driver, you have to implement a common signature. And so there's a signature for network drivers, a signature for storage drivers, for consoles, for system clocks, etc., etc. And for every target that we, compilation target that we implement in Mirage, we have implementation of this signature. So there's for Unix, for Zen, and so on. Last, we can compose. We can build higher level devices, which doesn't really know what are the underlying targets, but we can build that these as functors. I will explain that a bit later on. And finally, applications are as well functors. So system API. So for when you write a network card driver, what you have to implement is like this simple signature where you can write packets or you can listen for incoming packets. And like the implementation of these targets are only differs by how was implemented the signatures, and they only differs by how the devices are initialized. So, for instance, you can see that there is a connect function which takes the interface name, only the interface name for Unix, and for Zen, the connect function actually takes a domain and device IDs. Then when you want to build generic devices, for instance, here you can build like the Ethernet protocol handler, and so this one is built on top of a network card, which is passed as a Functor parameter. And lastly, the main application is as well is similar to a generic device, so it takes parameter low-level devices as Functor parameters. But the only difference is then they should implement an entry point, so a start function, which will be called when the application is started by the Mirage runtime. So here in the example here, like the hello Functor takes a timer, which will be provided by the runtime environment, because that's the time is a resource which is managed by the operating system. And finally, we can look at like a bit more complex application functor, which is like the Mirage website directly. And so this functor is parameterized by the TCP/IP stack to be used to send and receive packets. There's 3 different key value stores and a clock. So the key value stores are read-only, so they do not provide any write functions, and so user cannot really modify any files by construction. You can also notice that cryptographic keys, which are used for the TLS handshakes, are provided only in a separate store. And the last point is like the start function takes a few more arguments that in the previous example. It's actually one argument by devices, which is passed as parameters of the functor, and these values are initialized before we call the function starts, and this is the role of the Mirage runtime to do that in the right order. Right, so now that we wrote our application, how do we compile it and run it? So to compile it, we use the MirageOS compiler. So as a quick reminder, on the left, we have like the traditional layered stack for deploying applications. And on the right, that's a Unikernel way. So you link all the library code together and use a optimizing compiler to specialize the application and run it as single binary. And then the binary, there's no distinction anymore between user space and kernel space. Everything is in the same address space, and the only thing which is added to the application code is the OCaml runtime code as well. And so the sandbox that you picked can be anything, any kind of layer from the normal kernel, if you want to run it as a Unix application, or like an hypervisor, or like directly on top of baremetal, like RISC-V, if you like to. So using this kind of optimizing compiler leads to impressive results. So especially the OCaml compiler is very good at removing dead code for modules which are not used. There's even a patch which can remove functions which are not used. It's not upstream yet, but we're trying to make it happen. And so the resulting binaries are very small, as there is only the code which is needed to the application, which is embedded into the final binary. So for instance, it's only a few megabytes for a full system, which includes the application code, the OCaml runtime, and all the operating system libraries which are needed by the application. So you have to compare that to like a trimmed down version of Linux, for instance, where it's very hard to go below 50 megs for this kind of distribution. It's then very easy to move the application around, and then they can boot in very quickly in a few milliseconds. So instead of a few seconds like normal operating system. It's also very it's also use very few resources, so a few megabytes of memory, which is comparable to a normal Unix process. But again, it's not it's not like a normal Unix process. It's a full-fledged operating systems, which I think is very nice. So of course there are some drawbacks. So we simplified a lot the code, so we removed a lot of dynamic check that other operating systems are doing. But remember, we are doing that in OCaml, so actually the runtime checks become static checks, and they are not necessary anymore. Now I'll describe briefly the workflow that developers are using to create MirageOS Unikernels. So there are 3 steps. You write MirageConfig, then you make depends, and then do build. So most of the complexity of the Mirage command line tools, well, it's clearly only lies in the first step, because that's only where we call it. So this part is generating a lot of glue code, which is necessary for the other steps to work seamlessly. So let's look a bit more about Mirage configure step. So it works from, so first of all, the user has to write a config.ml file that we call an application manifest, which describes the application itself. So it says which device to use, how to configure it, what compilation targets are available. So we've developed a specific EDSL that we call Functor, which allows to describe functor signatures and to manipulate them as normal OCaml expressions. We can compose them, we can introspect them, and we can generate some blue code for the final application, depending on the desired configuration requested by the user. So let's look at an example. So like the classic workflow is to start writing your application for Unix, because that's like the simplest way to debug what happens. So you write your application, you use Mirage configure -- target equal Unix equals unit and -- net equals socket. And so that means that you want to compile your application for deployment as a Unix process using the socket API. So the socket API provided by the Unix kernel. And so the CLI tool will generate some glue code calling this kind of modules and functors, and assemble a big functor which will at the end call the start entry point defined by the user. If you then want, so okay, now you debug your application, it's okay, it works well, and now you want to try with the OCaml TCP IP stack, the one which is used by Docker for Mac. And so what you do is you change the -- net parameter to use the direct network stack. And so to do that, when you do that, you actually regenerate some glue code, which assembles the modules in a different way. This time calling the ARP library instead of, and you open like a raw network interface instead of using Unix socket. And the last step is once this is working again, you debug your stack, and then you want to run it on top of an hypervisor. So there is no Unix anymore. So the only thing to do is to replace the target argument from Unix to Zen, to rename the target argument from Unix to Zen. And so in that case, again, you generate a new graph of modules and functors, and then you instantiate the final application functor differently, only using Zen devices, and no Unix anymore. Right, on top of that, you have generated your workspace, where everything is, you have generated a skeleton of workspace, but there is still no, you don't have anything you didn't say anything about your dependencies basically. So you need to another step to pull all the dependency in. For instance, if your application is using a network driver, well, it doesn't use a network driver. You don't need to have installed any the TCP/IP package, for instance, the OCaml TCP/IP package. But if that's the case, you want the TCP/IP package to be installed locally. So there is some kind of dynamicity here that is handled by the command make depends. So in Mirage 3, when you call make depends, actually it shell outs to OCaml and install all the dependency via in your local OCaml switch, so that you can build your project. But we believe that is not very flexible when you want to build a final application. And so with Mirage 4, we introduced a new way to manage this kind of dependencies. What we do is we generate still an OCaml log file. And from the log file, we download all the dependencies locally, all the source code of the dependency locally. And then we prepare a Unix workspace where we set up cross-compilation runs. And so it's very easy then to compile the full source code, so of the application and all the dependency in one go. And so having this kind of workspace makes it easy to support more experimental targets. We have like experimentation going on with like ESP32, RISC-V, or WebAssembly. So the last step of the workflow. So you configure, you pull in the dependency with make depends, and then you can just do build. So that's a normal OCaml project, OCaml Dune project. There is nothing special about it. So everything that Dune is doing for like normal projects, the cache, cross compilation, everything is working properly. That works very well for C code as well, as long as it do not rely on glibc specific stuff, because we don't support glibc in Mirage, and as long as as long as there is no like Unix specific code in the OCaml code. So this workflow is very, I think, very nice. We would like to open it to the larger OCaml ecosystem. So we are releasing the project will download everything together into one workspace as a separate tool, which is called OCaml monorepo. We really would like more OCaml users to use it, and I think it will become like a central piece of the OCaml ecosystems in the years to come. Lastly, we also work on CI, because it's we want like people to start their project in Mirage and then making sure that they stay compatible with Mirage. And to do that, we need some kind of CI feedback loop, and so that's and that's related to everything that we do is as well usable by all the community. So this kind of CI will be available for everyone. Then lastly, we have so MirageOS is a set of libraries, compiler, and it's a runtime as well. So I will not go into too much details, but let's just look at how the Zen runtime works. So because it's a bit different for every target, but the general idea remains the same. So first, there's a sandboxing mechanism. So for instance, for Zen, it isolates every virtual machines from each other using some specific CPU instructions. But in any case, these virtual machines, in order to be useful, they need to access external resources. So in every of these sandboxes, there's as well a mechanism to create holes in the sandbox, and it connects on the two sides of the hole different things. So on one side there is like the virtual machine which wants to access the external world and doing I/O over that, and on the other side there's a monitor, which is usually a QEMU for Zen and for KVM and for like all the hyper virtualization mechanism. And so QEMU on the other side of the hole is emulating devices and connects the virtual I/O to the actual I/O on the host. So in practice, that QEMU is actually a large beast. It's more than 1 million lines of C code with a lot of known vulnerabilities, which leads to funny security issues, if you can call them like this. For instance, you can have like a bug in a floppy driver, can escalate into leaking private data from virtual machines. Even if the virtual machine doesn't have any floppy disk because it's a virtual machine running on the cloud, they still can access this kind of virtual floppy driver and then use that as a mean to gain access to other virtual machines. So for Mirage, it's defeating a bit the point of, okay, you simplify everything, but at the end you still have this kind of some virtualization layer or emulation layers, which makes it very more complicated than it should. And so we apply the same philosophy as usual. Instead of having something which supports everything, we want to specialize systems to reduce the complexity. And so we have developed with IBM Research a new monitor to replace QEMU, which is called Solar5. And the Solar5 Monitor is able to be specialized exactly to what the application needs. So for instance, if the application doesn't use any network access, we can generate a monitor which doesn't have at all this kind of virtual I/O exposed. And so no more floppy disk security issues. And so what is very nice about Solar5, it's a very simple API. There's only 8 syscalls. And so it's very easy to port to different targets. For instance, we ported to Zen, to KVM, but as well it works for the MUN microkernel. And so we believe that's a very good basis for like the Mirage Runtime because it's simple. We understand what happens, and it's portable to a lot of different systems and sandboxing mechanism. And as an example, we ported Solar5 like in the last year. We ported it to something which looks like Docker. So we using the Mirage compiler, we generate a normal Unix process, but we make sure that it's only use 8 syscalls, so very simple syscalls, no high-level ones like the opening a socket or something like that. And then when we do that at runtime, we can make sure that only these 8 syscalls are used by restricting the Unix process using Linux security subcom facilities. And so we think that this kind of the deployment runtime is very useful. For instance, when people are already relying on Docker images to deploy their services, and so they can allow them to deploy new Unikernel incrementally, or to replace existing services by Unikernel a bit more incrementally. Right, so I will just now focus on the last part of that talk, which is what we did on Tezos to make it work with Mirage. So spoiler alert, it's still work in progress, it doesn't really fully work, but we made a lot of interesting progress that I would like to report here. So first of all, we believe that the secure deployment of blockchain is today still a major challenge. And we believe that if we can manage to deploy Tezos nodes as Unikernel, that will have a big impact in terms of safety and security. So like there's some good alignment, let's say. For instance, Tezos is already written in OCaml. It's already using a lot of MirageOS libraries. And so we believe that making the effort to port the rest of the remaining of what Tezos needs to Mirage will help with generating more static, self-contained, and lean packaging images, and will be easier to deploy. And of course, we also believe that that will improve the security of this kind of deployment, especially for managing cryptographic assets. So yeah, the good news first is like 1/3 of the Tezos dependencies are already using libraries coming from the Mirage organization, so they work out of the box with the Mirage tool. And so if you look at the details, so they are mostly related to networking. So there's like HTTP and TLS mostly, and the storage. So like all the context, of course, VRMN. So most of the other dependencies are pure OCaml libraries. So it's rather easy to convert them to Dune, and we've done that work already last year. There are still some libraries which are used inside so Tezos itself is as well very well split between pure code and code which is using Unix resources, and so it's not too bad to port it to Tezos. There are still to MirageOS, but there are still like a few challenges, especially then the compilation part to Mirage is a bit more challenging. So first of all, so there are still a few uses of C code in Tezos or in dependencies of Tezos. And there is no support for cross-compilation in OCaml, and so that makes like porting this library to Mirage very hard. But as discussed before, we are addressing that by creating a new tool, OCaml monorepo, which will assemble a self-contained Zen workspace with all the source dependencies. And so as if the C code is using Dune, that makes like cross-compilation transparent, basically. So there's like, of course, there are some issues with like more complex dependency like ACL star, where the build system is not very amenable to cross-compilation, but we are working upstream to fix that. Second, there's like a recent, well, like a few months ago, we started to see some Rust code and Rust dependency popping in the repository, and so there is no support to So there is no support between no integration between Rust and OCaml, like between Cargo and OCaml, and so we managed to make it work for like some example, but it's very ad hoc, very hard to maintain because things are changing all the time, and so we are working very hard to basically fix that at the level of OCaml metadata. Making sure that the integration between Cargo and OCaml is fine, and then we can reuse that in Mirage to make sure that we track upstream changes. It's clearly as well something that the community start to need, and so we are working on that with them. There is also, as I said, there's while most of the Tezos code base is very well split in terms of accessing operating system resources. For instance, we managed to port a simple component like Tezos Signer. There's still a few usage of Unix primitive like fork in the code base of Tezos, and so this is not supported by Mirage and will never be. So there's various ways to work around this. So far, our preferred route to fix that is to make sure that actually so these kind of primitives will be available in the beta version in the OCaml multicore. And so we want to make sure that and Tezos is supposed to work on multicore like in a few whenever it's possible, and so we plan to add support for multicore to MirageOS instead. And so finally, Tezos is a very active project, which is great, but there's a lot of changes which have an impact on the support of Mirage, and so what we are doing right now is we are always trying to fix stuff after the fact, when we discover them, which is not really a great way of doing things. And so our current focus is to instead develop a very robust CI that we can use with Tezos, which will help us to maintain, to first make sure that we have like a working support of Tezos and Mirage, and to keep them working over time. So a quick example, quick timeline of the work what we've done so far. So we started two parallel efforts initially, like 2 years ago. One was we wanted to harden the security story around Solar5 because we had the security audits and that wanted to address everything that has been found, and so we spent a lot of time making sure that it was actually very secure. And we added two new deployments to Solar5 as well as a Zen virtual machine. So having the same kind of runtime for Zen and KVM make everything much more simple to maintain. And we as well implemented the seccomp Unix process to better integrate with the core deployment. We also started the second stream of work to try to port Tezos to Mirage. So as expected, while doing this work, we discovered significant gaps in the core OCaml tooling that we had to fix to make progress. So we ported a large part of the OCaml ecosystem to June. So it was, remember, we started 2 years ago, and it was not really the case at the time. We improved the support for cross-compilation of C libraries in June because it was not really working very well at the time as well. And we started to develop a new tool, which was Universe, called Universe System and not called Open Mono Repo, to better handle larger mono repository and to build single self-contained Zen Workspace and to integrate it with the OPAM software supply chain. And finally, what we are looking at, well, the next challenges are already described what they are, but I think some interesting things lie across integration with Rust and with JavaScript. So thank you very much for your attention. Please reach out to me if you would like to help on this project. As you might have seen, they are very ambitious and they touching a lot of components in the OCaml ecosystem, in Tezos as well, but in a lot of projects around Tezos, which will benefit from having this kind of consistency across them. And if you have any cool project that you would like to discuss with Mirage and Tezos, please reach out to me. And now I'm looking forward to your questions. Thank you.
All right, so now for the Q&A session, let's first send our asynchronous thanks to Thomas, of course. So there was the first question by Colin Gonzalez, who was, "Hi, I am the only one having a quite saturated sound. No, you're the only one who have a lot of sound issues. Hopefully there was a good trick, which was to use YouTube as a side window to get the sound, which I did use. I hope we can do some editing in the recording of this seminar so that people who watch it later will have a better live than we have. And then I proceed to work at the human text-to-speech component of this Q&A and read you back the questions. So we have a few actual questions. The first one were by our usual suspect, Jan Regisianas, asking first, why is using open standards reducing complexity? For instance, ASN1 is an extremely complex format. So who wants to answer this?
Yeah, I can restate some of the point that Anil's making. I think the difference with the complexity of a standard is that the complexity of a standard is composable complexity. You know, like if you commit to the complexity of implementing a unified. Sorry. Hello.
Great, go ahead with your answer. I think Benjamin is the only one that could hear it.
Yeah, sorry about that. Yeah, so I think the core point of this is that the complexity of a standard is a composable complexity. You know, if you agree to a consistent like a standardized format, then as your system scales, the complexity of the standard is the complexity that you have to meet the entire time, right? Whereas the alternative is if you don't have a standard, then your complexity is initially things look great because you specialize down exactly the format that I want, and then it's looking really, really smooth until all of a sudden I need to support something else. So for instance, like in the Tezos storage stack, maybe we want to support like a custom RPC like storage format, like a custom RPC format between different networks. Like that custom format is going to look really, really good for today's use case, but for tomorrow's use case, really not. And like Cat and Proto, although it has complexity as an RPC like interchange format, like committing to Cat Proto, that's going to support you for a much longer period of time. It's going to scale much better. So I think that's the core of why I would see the complexities being different there.
Yeah. One thing I was very surprised by is how usable ASN1 and X509 are when you have a reasonable programming interface as well. So before, my experience of ASN1 was using libasn1, the C library, and it's just a complete nightmare. Just lots of callbacks and unions, and it's a very low-level programming interface. So afterwards, when you have a nice combinator-based staged API as David Kalber built in OCaml, it becomes almost natural. So and you have this huge advantage that you could read decades-old tools can read the same format. So it's complicated, but they survive for decades. So the other thing to consider as well for something like a blockchain we would last for decades is that the standards just give you longevity. You know that X509 and ASN1 will be around for a very long time, whereas almost every other serialization format has adapted and changed over the years, right? So Captain Proto has 3 layers. We built support for that in Mirage. JSON RPC is there's never really been a standard for it. I've published the YAML libraries into OPAM for OCaml. I barely understand how YAML works. It's almost impossible to parse securely. So all of these protocols are endemic in the cloud. YAML runs Kubernetes, but they're incredibly hard to ascribe any meaning to. And I think it is important when you put stuff onto disk that it has meaning. So you know how to parse it and interpret it beyond the lifetime of the immediate processes that are running over it.
Well, thank you for your answers. I think that made a lot of sense. Before proceeding to Jan's next question, I'll sneak in my own question. So at home, I have a small part of my bakery system, Tezos bakery, of course, not real world bakery, which is a remote signer, which is a component, of Tezos. It's running on a small ARM machine, like a system on chip, Raspberry Pi-like. And on this system on chip, I have a USB hardware wallet plugged in to actually sign the blocks. And what I would like is to actually have the Tezos client running on MirageOS/baremetal on this system on chip, and actually continue to talk to the hardware wallet on USB. How far do you think we are from this?
So let me comment on what the process is to get there. The first thing you need a runtime of the bare metal, just something that gives you very, very simple access to the I/O and the scheduler you need. And then you need to cross-compile or natively compile, depending on your toolchain, OCaml freestanding to it. So OCaml freestanding is just the OCaml runtime extracted into an OPAM package. Once you have that, everything else is a library. So in Mirage, the scheme that Thomas described is that you link in all the libraries you need. So you grab all the Tezos libraries and you cross-compile all the C code. And then you just need a scheduler at the very end that will actually execute the thread. So we use LWT. So you just need to provide a bare metal LWT scheduler. And it's actually pretty straightforward. So the Zen one, for example, just runs with it just uses the underlying CPU, virtual CPU abstractions instead of select and poll as we do in Unix. So it's structurally very similar. It's just that the way that you block and you synchronize and you wait for I/O is at a lower level. And as soon as you do that, the rest of the time you're programming OCaml. So we've had several bare metal things running in the past. The difficulty with bare metal unikernels is that it's the maintenance of that layer, that hardware layer. So I built one ages ago for the first Raspberry Pi when we had the one-stage GPU loader and so on. But it's bit-rotted over time. Whereas in Linux, the device drivers are maintained, right? So other people are taking care of making sure that they continue to work. So there's been a bunch of really interesting work from the Unicraft team. And what they've done is build, they can extract out drivers from other operating systems. The Linux developers at Red Hat are also doing this. They've built something called the Linux library kernel, which where you can grab bits of Linux libraries, drive the hardware, and then jump to OCaml freestanding or any other unikernel from there. So that low-level bit is one step, right? If it runs FreeRTOS, as many of these USB sticks do, then you can run Mirage. Like it just works. You just have a cooperative scheduler with one core, and that's enough. Then it's a question of compiling the Tezos signer onto it as well. And Craig has been doing some work on this. I will pass the question over to him.
Well, yes. So the Tezos signer is like one of the first things that would make sense to exist in like a Mirage context, right? You want like a really low, like a small attack surface, and it kind of exists as a separate part of the code base from everything else. So you don't have to just port the entire storage stack to Mirage to get this to work. So I think when it comes time to start, once we have the CI in place for the OPAM mono repo workflow, and dot the I's, cross the T's for actually getting that thing so that it doesn't bitrot over time, that will be the first target, is getting like Mirage Signer to work. I think like when I was looking into like provisioning how to split up the Tezos code base into bits that make sense to do first. Like the signer is such a beautiful like little isolated bit of the code base that would make sense to deploy that. So yeah, that's top of the list.
Thank you. I'm looking forward to that then. So back to Jan's questions. So Jan asked, we are told, like in general, to never re-implement our own crypto, right? Some subtle bug found in OpenSSH, even though it has a lot of users. Why should we trust your SSH stack, right? Is it only because it's implemented in OCaml, which is cool, but maybe not enough?
Yeah. So, I posted the Unix security paper there. I was also taught not to re-implement my own crypto. Completely incorrect from whoever taught me that, because it has been common wisdom. But the reality now is that our knowledge of how to do specifications and verification against those specifications is much improved. So the fact is, we've gone from OpenSSL and Heartbleed, about 6 years ago now, I think it is, to having multiple performance equivalent stacks written in Coq or in F-star or other formal frameworks. So just a community of academics and engineers looking at this problem, deciding to fix it. It's only taken 5 years to get there. So that dogma is simply incorrect, I think. Now, when I first published one of the earlier Mirage papers, my PhD in 2007 was about rebuilding the internet using functional languages. So I rebuilt SSH back in 2004 in OCaml, which it still compiles fine. And the restructuring you get from it. So I think there's another question coming up with this as well, saying that if you build stuff in this modular style, is it just type safety you get, or are there more? There's a lot more. Modularity lets you understand the structure of your system, the components, the flows, and then it also gives you the ability to swap out these things to keep it alive. So the crypto stack is swapped out in SSH, for example. There's a bunch of key exchange upgrades. There's version exchange logic. There's a channel logic in SSH, which runs within the protocol. So you can open up multiple SSH channels to multiplex within one TCP connection. Well, I actually used that same channel logic from SSH in my Mirage TCP/IP implementation when I first started it, because I noticed that there's similar flow control and tokens and windows and so on. And that actually helped me do some networking research on some other work I published about how to evolve TCP, because rewriting this code in OCaml forced me to modularize the network stacks and look at them in a different way from the way you normally do it. And I think the same is true for crypto as well. Every time we re-implement something, sure, there is a chance to introduce new bugs, but there's also this great hope that you can actually come up with a new insight about how these very complicated bits of software that someone else or some other organization plugged together could look when you do it, and you do it for your purpose. And that's where actually OCaml hits a very good sweet spot, because modularity is something that no other language has. It's why I've programmed in OCaml for so long and why it's stuck with me. Even though I'm mainly an operating systems hacker, I've written more C code than OCaml code. But it's just modules. All of that hidden little hyperinference is all very nice, but the module system is absolutely beautiful.
Yeah, just to add, like to the why should you trust our SSH stack? The answer is you shouldn't trust our SSH stack, and I would encourage you not to. Like, it's great for me if people are skeptical about the code that I write, because it's all open source and people can review it and just like fix my bugs and complain about it, and that sort of stuff's great. So like, if you have the time, audit the code, please. Obviously not everyone has the time to audit code, as you know, the history of bugs in OpenSSH has shown, even like just in this example. I think, so that aside, I think you could maybe like somewhat understate the benefit of OCaml with regard to avoiding bugs. Like, it's not just avoiding buffer overflow, that's the problem. It's like in OCaml, you can solve a problem well once and then leave it for the rest of time. Like, this thing is solved. We know how to decode length headers, and we can do it correctly without affording to allocate, a 4 GB buffer. And, a lot of the OpenSSH issues recently, security issues, are like to do with parsing of network packets, right? Like, I'm parsing a network packet that says this thing is actually 400,000 terabytes in size, and then attempting to allocate that, or like giving a user a pointer into that. Like this is the kind of thing that, even though it still exists as a problem in OCaml, we can solve once, and then just rely on the compiler to like ensure that thing composes over time.
Thank you. I think it made a lot of sense. Maybe we could that, like in a more pragmatical way, we should trust your stack because nobody stole your Bitcoin already?
That's right. It's actually something I want to do with my Tezos Baker as well. The trick here is we challenge people to break into it and take our private keys. It's running as Unikernel, and if anyone does, then they will transact in the chain, and then we will know that they've broken into it. So these are kind of honeypots, public honeypots. So you can put your tokens where your mouth is and test the security. So our Bitcoins in the Mirage Unikernel never got stolen. I think there were 10 Bitcoins, worth quite a lot of money now. They're worth a fair bit of money then. And yeah, there's millions of attacks and never got stolen.
Cool. So let's change a little bit the question also. Elias has a question. It's also related to the wonderful modules in OCaml. So Elias asks, how do you take advantage of the modularity of Mirage for testing purposes? Like, do you have mocked network interfaces to test your Unikernels? And could we use those to spin up easily test networks in which we could inject network failures or things like this?
Absolutely. So I posted, as soon as you Mirage up your stack, testing becomes almost trivial. So we have several mocked up network stacks where you can connect up over fake bridges just using pure OCaml code, multiple Ethernet interfaces and so on, and then you can just create a function for failures in that bridge. So the README file for that shows you how you can manually assemble the functors required. So Thomas showed you how to automatically assemble things from specifications, but it's also very common just to manually assemble the stack just by applying functors. And then in Docker for Mac and Windows, for example, we use this technique to actually translate between Windows file systems and Mac file systems and Linux containers. So if you run Docker for Mac, you're actually running not quite this, but it's a very similar philosophy where we have a custom assembled proxy set of stacks that push stuff together. So every byte of network traffic and every file system access in Docker for Mac goes through this Mirage code, using tricks like this to either translate between operating systems semantically, or just to do a ton of testing. You can do distributed testing and stuff as well. So once we port the Tezos nodes to this, it should be pretty straightforward to have all kinds of deterministic and non-deterministic fault injection scenarios and incorporate fuzz testing. Because the really cool thing about this stuff is that it can just use AFL to fuzz the actual program now. There's no actual network traffic. It's all just function calls. So just running AFL against it will start fuzzing the full code base as any normal PL fuzzer does, without requiring dummy net and Ethernet bridge devices and the stuff you need to have for operating systems.
Looks very cool.
Yeah. It's not even just like plugging in a network stack. You can also just simplify your I/O module, right? So Roman Calasbeta, Dinosaur, he has some great work on this where he's written a library that parameterizes over I/O and parameterizes over LWT. And then in test, he can test like simpler aspects of it just by plugging the identity monad in as his I/O implementation. That's super cool. I love that. Like as a developer, the fact that I can have I can sit on top of a persistent storage stack and then plug in. I'm not actually using persistence in this test, so don't plug in a memory implementation of this thing and use identity monad as your I/O. My God, that's great. That simplifies so much of what I want to test from a top level. Yeah, sorry to interrupt.
Thanks. No, I did interrupt you. So I think it would be our last question because it will close at the end of the hour. So we have a question by Nick Wolonsky, which I find also very interesting, which is, beyond improving the security of Tezos, do you also expect some performance improvements as a side effect of Mirage and specialization simplification?
Yeah, performance is pretty much what is the next bottleneck, and generally speaking, there's I think the Tezos node is very sequentialization bound at the moment. So I expect that multicore in the shell is something we're working on as well. Will actually improve things quite a lot. But when it comes to specialization, we're already seeing this. The activating F lambda in release mode sped things up by about 30%, I think. So just inlining is going very well. You can think about Mirage as basically inlining external dependencies. So by doing these functor applications, you then allow F lambda and OCaml compiler optimizations to just activate not just for bits of logic, but also for configuration files. So the thing that'll be the most interesting is if there's static configuration that is currently baked into the code base, we can inline that further into the code base, and we should be able to see more and more benefits from formerly indirect calls becoming direct. An example in a TSP stack is if you're only listening in port 80, then you can do a little bit of partial evaluation to not have a hash table for listening ports. You're only listening in port 80, right? So just specialize the TSP stack to just ignore everything and then not keep dynamic track of things. So we can start doing things like that style of specialization. I suspect though that it then becomes very crypto bound, and for that we just need offload engines and stuff to improve that. So we'll see some. There'll be much more benefit from the simplification because debugging just becomes a lot more fun.